If we adjust the pitch angle here, we optimize airflow across the blade surface.
That aligns with the structural limits shown on the schematic here.
This cutaway view highlights the turbine section, where blades endure extreme conditions as hot exhaust gas flow generates the engine's power. These superalloys maintain structural integrity at temperatures where ordinary metals would melt or deform under the operational stress.
Readers. As you can see on the monitor, the conventional material is already showing significant creep deformation,
while the single crystal structure remains.
Slinjenes najvetek sidati brandsida в той просвет, Митяков унины цильцрикны и мигдабайтнатье цемыткой причастыми на экспилисы пестигдаль писыд затненицы.
Electro-discharge machining creates tiny cooling holes through the blade wall, each precisely angled to optimize internal airflow patterns.
Cooling air enters the blade root, travels through serpentine internal passages, and exits through film cooling holes.
Microscopic cross-section reveals the multi-layer coating system with distinct bond coat and thermal barrier layers protecting the underlying superalloy material. Testing demonstrates how thermal barrier coatings insulate the blade, allowing surface temperatures hundreds of degrees hotter than the protected metal beneath. Under ultraviolet light, any surface-breaking defects glow brilliantly against the dark background, revealing flaws invisible to the naked eye.
This irregularity here, highlighted in green, it seems consistent with a microfissure.
Agreed. We need to cross-reference the batch data immediately.
Coordinate measuring machines probe blade surfaces with incredible precision, collecting thousands of measurement points to verify complex three-dimensional geometry. Precision grinding operations refine the blade root attachment features, ensuring perfect fit within the turbine disc slots for secure mechanical retention. Fir tree root profiles are carefully shaped with specialized grinding wheels, creating the interlocking geometry that transfers tremendous centrifugal loads. Precision grinding removes tiny amounts of material from specific blade locations, achieving the exacting balance requirements necessary for smooth engine operation. Locking plates or pins are installed to secure blades within the disc, preventing any possibility of blade liberation during high-speed engine operation.
Tip clearances are within limits.
Confirmed. Specifications match the schematic. We are clear to proceed. Multiple turbine stages are stacked and aligned on the central shaft, forming the complete turbine section that will extract energy from hot combustion gases.
The installation torque on this joint seems low.
Checking the data now, it's within the acceptable range.
Visual confirms the condition looks good. Easy down, hold steady.
Alignment checks complete. Set her down. Acceleration is steady. We are green across the board.
Approaching critical velocity in 10 seconds.
Copy that. Maintaining pressure stabilization. Temperatures stabilizing within design limits.
Cooling system performance is validated.
Post-test inspection reveals turbine blades in excellent condition, thermal barrier coatings intact, demonstrating the success of manufacturing processes and material selection.
The elemental mapping confirms the segregation. This composition shows promise for high temperature stability.
Agreed. We should run a mechanical test on this batch.
Additive manufacturing equipment builds this prototype turbine blade layer by layer. Three-dimensional printing is revolutionizing aerospace component production.
These visualizations clearly show the accelerated oxidation mechanisms.
Precisely. Adjusting the yttria-stabilized zirconia coating should mitigate this corrosion.
Fatigue testing equipment cycles blade specimens through millions of stress repetitions, simulating years of flight operations in compressed laboratory timeframes.
The actual performance confirms the simulation results up to this threshold. This validates the analytical model's.
The deposition rate on this blade is holding steady at 98% efficiency.
That confirms.
Used blades undergo thorough cleaning to remove combustion deposits and contaminants, preparing them for detailed inspection and possible return to service.
The oxidation depth here is significant.
The coating degradation scan confirms it. This one is beyond refurbishment limits.
Repair processes restore serviceable blades with localized damage, using specialized welding and coating techniques to extend component life economically.
The root cause is clearly intergranular corrosion accelerated by thermal stress.
The corrective action is modifying the alloy composition and optimizing the heat treatment process.
FactoryVerse. Environmental testing exposes blades to simulated volcanic ash, salt spray, and other contaminants, validating bird strike testing validates turbine blade impact resistance, ensuring safe engine operation even after ingesting birds during takeoff.
Foreign object damage studies examine how blades tolerate impacts from runway debris, hail, and other objects potentially ingested during flight operations. Oxidation resistance testing exposes blades to high-temperature air for extended periods, evaluating coating performance and substrate degradation over time.
Thermomechanical fatigue testing combines cyclic stress with temperature variations, replicating the complex loading experienced by turbine blades in service.
Probabilistic risk assessment models analyze blade failure modes and rates, supporting maintenance interval decisions and fleet management strategies.
The instrumented blades provide real-time data during engine operation, validating design assumptions under in-service conditions. Machine learning algorithms analyze inspection images, automatically detecting blade defects with accuracy matching or exceeding human inspectors. Utilizing revolutionary turbine blade technology, this propulsion system is pushed to the extreme, enabling flight beyond Mach 5.
Combined cycle engine designs integrate turbine blades into propulsion systems operating across subsonic through hypersonic flight regimes. Aircraft turbine generators utilize high-performance blades to extract maximum power from compact turbine stages for hybrid electric propulsion.
Sustainable aviation fuel compatibility testing ensures turbine blades maintain performance and durability when operating on alternative fuels, reducing carbon emissions. Adaptive turbine blade concepts explore variable geometry features that optimize performance across different flight conditions for improved efficiency. By manipulating the boundary layer, these textured surfaces reduce aerodynamic losses, significantly improving overall turbine efficiency. Prognostic health monitoring systems track blade condition indicators, predicting maintenance needs before failures occur through advanced data analytics. These new field-applicable blade restoration techniques significantly reduce aircraft downtime and maintenance costs. Robotic inspection systems automate blade examination processes, improving consistency and enabling inspection in confined spaces difficult for human access.
Blockchain technology creates immutable records of blade manufacturing and maintenance history, enhancing traceability and supporting certification requirements.
Sharing our computational fluid dynamics models accelerates the design phase.
Exactly. The cooperative development program relies on this data exchange.
The fatigue life of this alloy is significantly higher near the leading edge.
We need to verify that against the stress analysis.
Industry standards organizations establish specifications ensuring turbine blade quality and safety across manufacturers and operators globally. The stress analysis on the blade root geometry looks optimized. Yes, it meets the safety factor requirements for the new standard. Supply chain management coordinates the complex network of suppliers providing raw materials and specialized services for turbine blade production.
We evaluate investments in advanced turbine technology, balancing manufacturing costs against market demands to maximize ROI.
Environmental assessments measure turbine blade production impacts, driving sustainable manufacturing practices and reducing the industry's ecological footprint.
These manufacturing techniques are essential for the turbine blade's longevity.
And this specific geometry improves the efficiency, correct?
Technology transfer initiatives commercialize research advances, bridging the gap between laboratory discoveries and production implementation in operating engines. Intellectual property portfolios protect turbine blade innovations, enabling manufacturers to recover research investments while advancing technological capabilities. Market forecasts predict turbine blade demand across commercial, military, and industrial gas turbine applications, guiding strategic business planning. This analysis highlights differentiating features in turbine blade materials, cooling technologies, and aerodynamic
Critical incident protocol activated. All teams report status.
Team B confirms blade damage on Turbine 7.
Copy that. Containment procedures are now in effect.
Legacy engine support maintains turbine blade availability for older aircraft, ensuring continued safe operation while newer models enter service.
Obsolescence management addresses discontinued materials and processes, developing alternatives that maintain blade performance and certification status.
Dual-use technology considerations balance turbine blade advancement with export control and national security concerns for sensitive aerospace technologies.
All right, bring it back 20 feet. Easy now. Clear on the right.
Continuous improvement programs systematically enhance turbine blade manufacturing processes, incrementally advancing